So let's suppose that we've got a big old hunk of silicon. It's not silicone. Silicone is a rubber, right? Silicon is the elemental form of, well, silicon. And we put some chemicals in it or dope it such that it has a deficiency of electrons. A deficiency of electrons just means that it has a bunch of something called holes or spots that electrons could go. And so we call that a p-type material. It's p-type because it's kind of a positive material. It's got a bunch of pluses. Remember, electrons are negatives. So it's got a bunch of voids where electrons aren't, and so we kind of consider that to be a positive charge, and so therefore this whole thing is p-type. And now let's suppose that we added some regions in here. Actually, let's go with purple. We added some regions in here. One right here and one right here. And we made them n-type. So we'll say N and N. So that means that there's an excess of electrons in these zones. Now, what do we know about charges? And how do I want to say this? Well, we know that charges that are different attract. So that means that on these edges here, you've got a bunch of pluses coming here and a bunch of minuses here. And initially you have a little bit of motion going on here, right? You got the pluses and minuses pairing up. And what it actually does is makes a barrier along this whole border. Same with this guy here, a barrier. And if I were to hook up, let me remove that now. If I were to hook up a wire here and here, and I were to try and make current flow this way, meaning that I had plus here and minus here, what would happen is I would actually not be able to have my current flow through this because these barriers that form are impassable. The barriers are impassable. So what we can do, or what we do in this type of transistor, is we add in we make a little plate here. And this is an insulator that we're adding on here. A little insulator, meaning that nothing will ever be able to conduct through it. This N-type and this P-type, these are called semiconductors, meaning that they can conduct or they can't conduct depending on the way they're configured. That's what silicon is a semiconductor. And the stuff that we dope it with is also a semiconductor. Well, that's not entirely true. This whole composite material acts as a semiconductor. Now let's add a metal plate on top of this. It can just be a thin metal plate. And we have another wire on here. And now let's say we applied a minus here. If we applied a minus voltage, meaning that we have an excess of electrons on here, or you can almost think of this as a P material for the time being, what's going to happen, this is an N material, you could think of it as. What's going to happen is these pluses are going to get attracted and all hang out by this plate. They're going to want to try and get as close to that plate as possible because we've got a negative here and a plus here. So they're all hanging out and they're making it really hard for current to flow through here because we've also got these little barriers built up. But then if we switch this to a plus, if we switch it to a plus, what's going to happen is we kind of have this spot that opens up that pushes away other pluses. Remember, like charges repel. And these pluses, even the ones on this border, are going to move out of the way. And that makes this like an N type of material. And if we have all the same type of material, then current can flow through. So when this is a 0 or this is a minus, current cannot flow. When it's a 1, current can flow. So let's break this up here. So this is we call this our gate. And really, to me, that's the important one. If our gate is a plus, then we'll say current. If our gate is a plus, then current flows. If our gate is a minus, then it doesn't flow. Don't know how to spell doesn't. Oops. Oh man. So this is kind of our behavior here. And of course, these guys also work in this kind of in-between area where if you transition to points between full plus and full minus, you can get some interesting behaviors. But that's not what we want to look at for digital cases. You want to just look at on and off. So you can also think of this as a switch, just a switch that can close. So we've got our two terminals here. And if current doesn't flow, that means the switch is open, right? It's like you've taken a wire and disconnected it. Current can't flow through it. But if it does flow, that means we've got a wire that's connected or shorted here. And so we can also call this we could actually look at this as infinite ohms for when it's open. We look at it as 0 ohms when it's closed. Of course, it's not actually 0 ohms, but it's close enough for what we need to do in terms of digital circuits. So this is the kind of really crash course of what an NMOS transistor is. You can get way more into what goes on inside these transistors. But the real thing is this table right here. This is the important part. In terms of digital logic, if we apply a plus here, so that could be a positive voltage, maybe like 5 volts, and then this could be 0. So I'm going to say 5 volts, and then we'll say 0 here. We get this behavior. And so our symbol for an NMOS transistor, if we want to look at our super simple symbol, it looks like this. Where this is our gate. And so these are just the two terminals. If you really want to get specific, this is the drain and this is the source. So this is the drain and this is the source. So this is the symbol that we typically draw. And you actually see that this kind of looks comparable here. Actually, we've got this, the gate has this plate here and it's isolated. So it's actually almost like the symbol for a capacitor when you really look at it. It's because that's actually kind of how this functions here. This gate kind of functions as a plate on a capacitor. So that's the NMOS transistor in a nutshell.